Yeah, thanks a lot, Andre. A great intro. So today we're going to be talking about scalable digital doubles. So let's first have a look at what we mean by digital doubles. So here are some great projects that I really like from the past recent years. And all of those people here that you see are actually not real. They are CG models. But they look very, very, very close from some people that exist in real life. So actually, a few days ago, there was this demo Enemies that came out by the Unity team. And I would engage you to do two things. So first, look at this still and appreciate the quality of the shadows, the quality of the eye, the skin. And then I'm going to play the video, and then you can maybe focus more on the motion.
Power is given only to those who dare to lower themselves and pick it up.
So really fantastic work from that team. I mean, that looks amazing. Then one question is, can every single one of us get access to this type of quality of digital double, and potentially also, can all of us drive those things easily? So to try to answer the question, one thing we can do is to look at how those projects came together. So here you have Siren and the DigiDog. And one common theme is that those projects are the outcome of great collaborations from industry leaders. So you can see here some great names, Trilateral, Qubit Motion, etc. And if we look a little bit deeper, there are some themes that emerge. So one theme is enrollment. How do you go from someone real to a photoreal digital version of themselves? But also tracking. So like for instance, if you look at Doug here in the top right, so he has this mouth motion. How do you go from here, him making this motion in reality, to that transferring to his avatar? And finally, how do you render this posed avatar with this face that he's making in real time? So looking a little bit deeper in terms of enrollment, like how do those projects do it? So here I'm going to show you a short clip that's from the ICT, and they have a great light stage there. And this is part of the data that's being used to enroll here for the Meet Mike project.
3, 2, 1, go.
So as you can see, what you can do is multiple things. So capture the actor from different viewpoints, of course, different lighting conditions, etc., and then capture a wide array of data about the actor. But when we look at what that really means for you and I, like, can we access this type of hardware? Well, the answer is probably not, or not at scale at least. And then how do we go from all that data that you see here in the bottom left to that high quality digital double here in the bottom right? So part of it is automatizable, but part of it is also very labor intensive, especially for artists. The next theme that we saw emerging was tracking. So here we're going to quickly listen to Doug, and he's going to be describing to us how he's driving his digital counterpart, so the DigiDog.
I'm wearing an inertial motion capture suit that's figuring out what my body is doing. And I've got a single camera here that's watching my face and feeding some machine learning software that's taking my expressions, like, and transferring it to that guy.
So great stuff. I mean, the motion fidelity is quite high. But here again, it requires some custom hardware. It takes some time to put on, as you can imagine, those suits. And also, do we want to wear those like fairly big headsets for an extended period of time? The answer is probably not. I mean, that works really well for the scenarios they are interested in, but probably not for you and I. And the final theme that we saw was rendering. So, like in particular here, if we look at the demo again, Enemies, so they use like very high-end graphics card, top of the line, for real-time ray tracing. So can all of us do that on desktop? Maybe, if we can afford it, but certainly not on laptop or HMDs. So putting it all back together, so we have those three themes. The last one, rendering, I'm not going to be touching upon it in this talk. My secret hope is that more and more will transfer to the cloud. And we're going to be focusing on enrollment and tracking. And of course, the goal is not to do a complete 180 degrees compared to how those problems are approached by those great projects, but to get inspiration from them. So let's first talk about tracking. So here, this is a project that Sade, who I believe is working, who is going to be presenting right after me, is going to be presenting more in detail. But this is Tom, so here wearing a HoloLens. And as Mark described earlier, so this HoloLens gives us a few things, like in particular hand tracking, but also head tracking. And using inverse kinematics, you can put that on an avatar that you see here next to Tom. So one thing that is quite obvious here is that the facial expressions that Tom are making, so here in particular he's speaking, like his lips are moving at least, they are not transferred to his avatar, as you can see here. So this particular problem we are working on in my team. And the pipeline that we follow is fairly standard, at least like from a first look. So we take an image of someone, we compute landmarks. So here the secret sauce is actually there, so we compute very, very dense landmarks, many, many times more than the competition. And that allows us to predict this, let's call it the blue face for now, prediction that comprises a few things. So the identity of the person, his expression, and its head pose. So those things are actually fairly traditional. Like there is nothing fundamentally new to what we're doing here. And actually, the projects that I highlighted earlier are also doing some of that. They are building rigs that are highly personalized to the actors. So they would do pretty much only, let's say, a focus on the right-hand side here, expression and pose, to get very, very high fidelity of motion. And here in comparison, here we want to scale. So we need to be able to handle different identities and hopefully like a wide variety of them. So here you see some samples that we have from our model. So that is variety across ethnicity, age, and sex. So similarly to those other projects we talked about earlier, we also do need some artist input. So here in particular, we use them for crafting expressions. But you can see them as done once and for all. It's like for this generic model. We don't need to do them on a per user-specific basis. So if you recall the pipeline I was presenting at a high level, we said, OK, so the secret sauce are those dense landmarks. So how do we train for them? So the first three columns here are pretty much what we just talked about. So this explicit surface model, on top of which we can add texture, hair, clothing, props, and of course define how we want to light this scene. So it can be any type of lighting. And that allows us to render a lot of images for cheap. And because we are using synthetics, the huge advantage here is that we can extract ground truth for free. So some of that ground truth could be depth maps, albedo maps, normal maps, I mean, you name it. But here in this particular project, we're very interested about those landmarks. So here is what you see on the right side. So you can think about them as a subset, let's say, of this blue face, subset of the vertices of the blue face that you saw earlier. So when we put everything back together, so this is what we have today. So a couple of things to notice. So first, this is running off a webcam and in real time on a single core of a laptop. So that's what you see on the table here. And the yellow stuff that's displayed on the actors are those landmarks, but just joined by lines. And then you can here appreciate the quality of the motion being captured, head pose, etc. So we just covered how we can potentially tackle tracking the full body, but also the head. And the other big theme that we said we would talk about is enrollment. So here again, enrollment is how do we go from someone that exists in the real life to their digital counterpart. So this is actually an illustration, doesn't come from any of the previous projects I was describing, but I think helps describing the process. So we said this enrollment stage, some things can be automatized, some things are usually requiring a lot of artist input. So some of that could be, for instance, designing the hair look, designing here the eye. Maybe we can talk a little bit about that, the eye of the subject. So the projector is not pumping so much light here, but maybe you can still see what's at play. So you would have the final eye rendered on the rightmost side, and then the artist decomposed this eye in a couple of pieces that exist also in reality. So you have the sclera, so this big ball. So we are starting from the right, where you see the white part of the eye, but also all the small little veins, and on top of that you have the iris, which is unique to each of us, and then the cornea that has a lot of reflectivity in the eye. And a few other things, you put that all together, and you can see the eye on the right, where there are some interesting details that the artist took the care to introduce. For instance, this watery eye. I mean, you see a little bit here. And this is this type of details that separate an avatar that looks a bit uncanny to an avatar that starts to look real. So quite cool work, but also a lot of dedicated work for building one specific eye. So the question is, can we actually go without that? Like, could we go from observations, so from data, like here some scenes, to being able to capture with high fidelity all the material properties of the scenes in question? So on the left side here, you would see, for instance, some caustics that are very well captured. So looking, for instance, for details around the glass. And on the right, you see a wide variety of materials. You see trees, green vegetation, a car, reflection, refraction, the ground, etc. And this piece of work was quite groundbreaking, and it's called NERV, and was introduced in 2020. So visual quality is great. So this is the output of their system. So this is completely machine learned. A couple of drawbacks, at least in the original publication, so that deals with only static scenes. So of course, when we want to deal with human, that's going to be a problem, but we're going to be talking about that in a minute. And also this renders in seconds, so way off what we would need for interactive systems. So this particular problem of rendering time, this is what we addressed here with a work called FastNERV that we published in 2021. So you can see here that's NERV, what we would take to render it by default at 30 hertz, let's say, and the resolution that we would need to do that, and our work on the side, right side here, that renders way over real-time rates if we wanted to do, for instance, webcam control. So cool. Let's look at quality quickly, side by side. So you see here on the left side, this previous work, the original work, and on the right side, our work. So hopefully the visual quality that you will observe is largely preserved between the left and right. Of course, modulo the speed, which is the big gain here in this work. So this is fast now. Okay, so we can render static scenes fast, but they are still static, as I said. So how do we go to humans? So here, I would encourage you to do the same critical exercise as before. Let's look at this static frame. And before we do an analysis or a detail about what's going on here, just want to mention that this is very recent results that only has been enrolled on one frame. And look at, for instance, how the eye look like, the skin look like. And then in a second, we're going to be listening to Paul and maybe here focus more on the motion. At some point, I'm also going to be pausing the video so we can discuss some aspects about the results.
So one of my favorite pastimes is skiing, snowboarding. I actually took it up quite late. It was in my third year of uni. Some friends were going on a uni ski trip, and so I joined, and I kind of had to think about whether I wanted to do skiing or snowboarding, and decided just based on the number of lower body injuries to knees and things that I would go for the snowboarding.
Oop, I just wanted to pause this one. Maybe I can just put it in the middle again. So what we can see here, so of course there are a few things that are obviously missing that we're working on right now. For instance, the mouth interior is not there. You can also see that the dynamics of the mouth, I can replay here without the volume, are okay, but you can definitely see that there is something missing. So this is driven purely by this face tracker that we talked about earlier. So when we build those face trackers, we are trying to capture almost everything about everyone. But of course, that means that the subtleties go away. And you can see that, I think, especially around the mouth here, and maybe a little bit also around the eyes. So where do we want to go from there? I think there is tons that we can do. So this is based on some inductive bias that's called volume rendering. But there is so much more that we can do. Like, this is purely machine learned. There is no prior about pretty much anything here. But if we look back again at those very successful projects, like Enemies, for instance, well, they do a lot that is very prescriptive. Like, for instance, when we looked at how the eye model would look like artists would be defining what reflectance model to use. And this type of knowledge, because we work here with faces only, we could also use. And with that, I would like to thank you for attending this talk and opening for questions if we have time for any.
Yeah, so we definitely have time for questions. Anyone? Okay, maybe let me ask you, I mean, I guess there are those classic problems like rigid hair and these issues that you definitely will love, but what are the other challenges that you see with this technology?
I mean, that's a very good question. I think maybe we can talk about hair a little bit. So here you can see it doesn't look great, at least from my point of view. I mean, this is partly because we don't have good lighting, but that's our fault. The second bit is, of course, physics. So in that Enemies demo that you saw at the beginning, the hair is actually simulated in real time, so it looks great. Right now, what we do is not at that point yet, but please keep in mind that this is active research. So definitely, this is not doable right now. A lot of what we then need to focus on is how do we make this look good temporally. So maybe if we look at some statics randomly, it starts to be convincing. But as we saw earlier, the dynamics, I think, is one of the big problems for us today. So I would say maybe focusing on the dynamics. So this person, Paul, then hopefully will look like Paul in the way they move in the next few years.
So one of the things that's striking to me is the fact that this avatar is not, his eye gaze is not focusing on a particular thing. It's wandering all around as if he can't see. And do you have any thoughts on, because I think that would be pretty compelling if you could solve that, as if he's talking to someone or at least addressing.
Right. I think part of this demo, unfortunately, is like maybe misleading. So I should have mentioned. So there is the actor speaking, and then we have the camera traveling. So indeed, like we could have had a much better version where the actor is looking at someone else, and maybe that would have conveyed that. In theory, we do have very precise eye tracking. So Mark talked about some of that. So in HoloLens, it's like pin sharp. And we have control, like very precise control in this model about the eye itself. So in theory, like we can control it to look exactly in your eyes. So speaking about eyes, one thing is that because here we enrolled on one frame, all of the specularities, like they stay fixed, more or less, which is definitely a drawback and will look a bit weird. Because as we've seen, like as the user looks around, maybe I can do it from here, like the eye moves a bit, but like the appearance should move, like the glint should move. So eye contact, I think, definitely possible, especially if we leverage the eye tracker from HoloLens.
Yeah, I think it's more than eye contact. It's also the way it's saccading. The saccade.
Right, so this is absolutely correct. So right now here there is no saccade, but I believe, maybe Mark can comment on that, but I believe that the eye tracker of HoloLens is high frequency enough to track this. So this can, again, if the tracker is fast enough, like this type of model can like just replicate it. There is some matter, of course, of doing rendering with motion blur and things like this. There is more, of course, that need to be added. So right now here, there is no motion blur at all in those renders. So you're right, like all of those very subtle things that make us a human, a lot is missing here. So maybe we can argue that the appearance is getting there, but definitely the motion needs a lot of work.
Yeah, my second question was about micro expressions.
Right.
Right, how we do that, so.
Okay, any other question?
Yeah, thank you for your presentation. I wonder, is it possible that like we can make digital avatar or twins that are driven by action? For example, you know, like here, I'm here and I'm like constrained by this physical location. And then let's say I want to transfer me to other room. And then there, probably the physical constraints must be different. And I want to, let's say, walk through like from back to front, but in there maybe there is some like obstacles, and then like maybe if we know some action labels, then in there maybe the digital twin can move a bit different, but do the like same action. Is that possible? Do you think? Or?
Right. I mean, like this is a very good question. This is pretty much out of scope for this particular work that we're doing, because we are trying to, in a sense, replicate everything about the user, like how they, like their expression and how they move. But of course, in theory, what you describe is possible. Like one can do, and there is a lot of work in this field right now, like try to like simulate motion around, you know, like obstacles, for instance. And then like we can then take those controls and then transfer back to that rig, in a sense. So in theory, yes, but unfortunately, I don't have anything to show you on that front.
Yeah, thank you so much.
Hi, so I just wanted to ask, now you use basically visual tracking for animating the avatar, but did you look into other modalities like speech? Because I know NVIDIA is working a lot on that, like speech-to-face or something like this. So I wonder if you look into that, and if not, would that help actually to add some realism towards that?
So this is a good question. I mean, for me, speech will get you only so far. I mean, probably what you can do, like without, you know, like crossing the boundary of trying to infer, you know, like emotional state, is probably like limited to Visime, so the mouth region. Then the question becomes, how do you control, you know, like here the forehead of the actor or the eyes? I mean, like, at least as far as I know, it's not obvious to control that from audio only, because like audio only comes out of your mouth, and then that's the only signal then that is, I guess, preserved about the state of the face of the person. It's like what the mouth is doing. And also, to some extent, as far as I know, there is not a bijection between audio and mouth pose. Like there could be multiple ways to explain the same thing. So NVIDIA is doing a great work. I believe that there is emotions that you need to pick in that tool that make it look good. But at least in our team, we are trying to not cross this boundary. We don't want to try to predict the emotion of the user, because that can lead to, you know, like for instance, you and I are in a call, and then maybe your avatar looks angry where you might not be angry. And then what does that mean for me? Like, do I see you as, you know, like not receiving well what I'm talking about? Or, so it's like a subtle barrier. So of course, you can do a lot with speech. Can we do better lip control than this with just speech? If the answer is on the fidelity side of things, I would say probably not. But if it's on the realism side of things, like do the mouth look, I mean, move well, then I would say yes, probably. But beyond mouth, I'm not sure that signal just by itself can be used. Right? It's like you need to see, or to get more signal or more modality.
But what about merging both modalities, like your visual tracking plus speech? Because I think that's basically kind of solving some of the both issues on both sides.
So this is a very good question. I mean, I can see that very useful, for instance, like if I speak like this, right? Like, of course, the webcam doesn't see anything about what I do, but the audio still senses like what happens in this area. So this is an active area of research internally. But again, like these prototypes, they were purely off vision tracking. So there is no merging yet, you know, like clever merging as you describe, like for instance, where the mouth is occluded. So that I can see being like a great scenario where leveraging both could shine. Yes, absolutely.
Thanks.
Okay, so maybe we can have last question.
Thanks. So what role do you think physics knowledge has to play in this? So do you think there's useful to feed it into the dynamics or the lighting or whatever, or do you think we just learn it all?
I'm actually a big fan of using physics for those things. So, but that's my angle. So I would say yes, using more physics would be something to do. And right now we do very, very, very little on that front. Like for instance, if you look at how like we move in space. Like for instance, I don't know if Sadek is going to be talking about that, but maybe a quick note on my end there. Like if you have like very sparse observation of you, like for instance from HoloLens, you still need to be able to walk, but at the same time you know that you need to obey physics. So that means obeying friction constraints, penetration constraints, and a lot of physics, or constraints that we can explain through physics. And yes, a lot of that can be leveraged. Like the basic way to put that together is, okay, let's use RL, and you have like a physics simulator that, I don't know, like maybe simulated through a PD controller, iterated many times, converges to something that's realistic, and then feeds you back information for your system. And yeah, I'd love to do more physics, absolutely.
Okay, so let's thank the speaker.